In this video, what we're going to do is go through some of the properties of limits as well as set you up for being able to do some limit problems. So we've already discussed what a limit is together. Remember, a limit, it's just a tool. Now your math classes, remember, are going to have discussed this in a very different sort of way, but it's a tool for us to predict how a function behaves at a specific point in the domain without evaluating the function at that point. Right? So remember, it's our way of looking over the edge of the Grand Canyon without jumping in. It's peering into the abyss without plunging your head into it, right? And we said that the limit exists as long as the function exhibits the same predictable or prediction from quote-unquote both sides, right? That examining the function from the left and from the right would yield the same answer. Then we would say the limit exists. And if it gives you two different predictions, then the limit does not exist, okay? So remember, for the vast majority of functions, for continuous functions, for example, if f of x is equal to x squared plus 4x plus 2. We know that if I take the limit of that expression as x approaches, say, 0 of f of x, that is going to be the same thing as just plugging in 0 there. And so in this case, that would be equal to 2, right? So if I apply the limit operation to both sides of this, technically what happens here is the following. Right? So I say the limit as x approaches 0 of f of x is equal to the limit as x approaches 0 of x squared plus 4x plus 2. Technically, what's happening here, folks, is that the limit operation distributes across the addition. Right? The limit as x approaches 0 of x squared plus the limit as x approaches 0 of 4x plus the limit as x approaches 0 of 2, right? And then each of these has predictable behaviors, right? No matter which direction you come from, because x squared is a continuous function in this region, has no weirdnesses from it, no jump down discontinuities, no point discontinuities, no asymptotes, no cusps, right? We know we can just plug in for these things. We don't have to be very complicated there. And so that gives us 2. But knowing that I can distribute that across the addition is helpful. Why can I distribute it across the addition? Because, just very simply, the limit operation can independently figure out what's going on with each of these 3 functions, and their value at each of those added together is the value of the composite function. So nice and simple there, right? That you can distribute the limit across addition. But so that's always going to be our first go-to, right? That when we have a limit, we plug in and hopefully we get something that works. But then sometimes nature is not as kind to us. For example, let's say we have f of x is equal to x squared minus x minus 6 over x minus 3. Okay. So take a minute, take out your TI-89, graph that function. Hopefully, when you graph that function, what you found out is that this is a linear function that has a y-intercept at 2 and has a deleted point at x equals 3. This is not a pretty graph, but there it is. So that is a large deleted point. That point should just be one small little mini part of the domain, but there it is. So this should, if we notice, this should have a limit. Because if I just looked at this graph, we could tell that this thing has predictable behavior at x equals 3, right? That as I approach this from the left and approach this from the right, there is some element of the range that corresponds with this. But if we plugged in at 3, we'd fall into the little black hole here, right? So just looking graphically on your calculator, you expect the answer to this to be 5 if we were to examine the limit at x equals 3. But here's the problem. If I do this, let's examine this. The limit as x approaches 3 of f of x, right? If I were to just plug in, well, 3 squared minus 3 minus 6 over 3 minus 3, you'll notice I get 9 minus 3 minus 6, which is 0 over 0. Uh-oh. What's that called? That's called an indeterminate form. And anytime you just plug into a limit and you get an indeterminate form, you need to do something else in order to solve that problem or to discover that that thing has no limit. Now the graph tells us, because there is predictable behavior, that this is going to absolutely have a limit. So what can we do? Well, one thing we can always do, remember, the always backup is what? The always backup is to numerically evaluate the limit. I know it's not fun, but it's always nice to know that there is a blunt force tool that always works. So let's remember our standard for numerically evaluating a limit, as terrible as it is. What we're doing is we are going to pick values of x, 3 above and 3 below what we care about, and find the values, and we're always going to pick let's see, if 3 is the number in question, we're always going to pick 0.1 below the value in question. We're always going to pick 0.05 below, and we're always going to pick 0.01 below, and then the same amount above. Now, this is the same thing that you're doing in your math class when you're doing it using the delta and epsilon notation where you're finding neighborhoods and ranges. We're just evaluating this very numerically and practically rather than in that theoretical sense. But remember that idea in your math class is getting closer and closer without being at, and having confidence that f of x is getting closer and closer to the same value. So you can turn off the video for a second and calculate all of those values for me while I grab my calculator, which is in the other room. Great. I probably should have calculated these values ahead of time so when you turn the video back on, you had them, but there it is. So if you just want to fast forward through this while I'm just plugging in numbers, feel free. I won't be offended. Right, and so we're getting here 4.9. Okay, 4.95. Okay, fairly predictable behavior here. And this is 4.99, okay, 5.01, 5.05, and then 5.1, okay? And so what we notice here is that as I approach 3, the value here approaches 5, and as I approach 3, the value approaches 5. If I want to write it this more formally, the limit of f of x as x approaches 3 from the left is equal to 5, and the limit as x approaches 3 from the right is equal to 5 as well, and therefore I can say, because those two things are the same, that the limit as x approaches 3 of f of x is equal to 5. Whew. Now that's a lot of work, but it always works. Remember, the numerical evaluation is our blunt force, brute force method that always works, and this is what it needs to look like every single time. You're testing 6 values, 3 above, 3 below. You're making a statement about what's happening from the left, what's happening from the right, and then you're making the overall statement of what the limit is equal to, or you are saying then if these two things are not identical, DNE if they're not identical. Okay, great. But that's just terrible. I don't want to do that. You don't want to do that. So what we can always do when we have a function is we can transform that function. Now here, a simple transformation of a quadratic function is just to factor it. So if I factor that, that becomes x plus 2 and x minus 3 and x minus 3. Oh my God, look at that. Boom, boom, there goes my deleted point. So if I now take the limit of f of x, limit as x approaches 3 of f of x, I'm just going to show that evaluation of 3 plus 2, and I get 5. There's my answer in one step. So boom, there we go. So the first thing we should always do when we're doing these is see if we get an indeterminate form. If we do get an indeterminate form, see if we can transform the function. If we can transform the function to get rid of the indeterminate form, then plug in, awesome. Sometimes that's not going to work, but that is a good thing to do. So there we go. So let's talk about some other things that we can do as well. And I will show this. So here we go. Some other limit rules. So the limit as x approaches, say, a of some constant times f of x is equal to, as we saw in the previous example, just the constant limit x approaches a of f of x. Right? It's like the limit operation doesn't really even act on that constant because it's multiplicative and it can pull through, right? So that's really nice. Kind of a corollary to that, really where this comes from, is if I take the limit as x approaches a of f of x times g of x. That's a composite, not a composite function, excuse me, but that is a product of functions is equal to the product of their limits. And so let's talk about that for a second, because that's going to be really critical in a couple of minutes. So why is that? Well, remember that the answer of a limit produces a value, right? And so when you multiply functions together, when you plug in values of two functions, say for example, x and x are my two functions. If I were to plug in 3, 3 and 3, I get 9. It would be the same thing if I took the limit as x approaches 3 of x and limit as x approaches 3 of x, and I would get that same thing. Because the output of a limit operation is a value, I can simply multiply those values together. Now, your calculus classes are going to go in a much deeper way into that proof, but that's a sufficient sort of logical proof as to why that works. Now, if you think about it, that's the underlying structure of why this one works, because if I take the limit as x approaches a of a constant, well, the constant doesn't vary, and so it just is like almost that this just becomes whatever that constant was if this was the constant. So there it is. Now, the reason why this is helpful is because f of x and g of x could be the product of two functions. They could also be the quotient of two functions. Like if f of x was x and g of x was 1 over x squared, it wouldn't matter, right? So I can distribute the limit not only across addition, but also across multiplication and also across division, meaning act it separately in the top and bottom. Now, that's going to become important for some sample problems that we'll do later. Okay, so if I have a limit, first thing I do is plug in. If it doesn't work, indeterminate form, see if I can transform the function. If the transformation still doesn't work, I would go into doing a numerical evaluation. So let's do one more example of that. So let's say our function is f of x is, I don't know, 1 over x, a nice simple function there. And I want to take the limit as you can guess, as x approaches 0 of 1 over x, okay? And so what do I get there? Well, if I do that, I get another indeterminate form, right? So if it's an indeterminate form, what I want to do is see if I can transform it. Oh, I can't transform it. So I would go to a table, x and f of x. Okay, so here we go. And so 0.1, 0.05, 0.01, and then negatives. I probably should have done the negatives up top to tell you the truth, but I don't know why I didn't. Cool. So if I plug that in, this becomes 10, this becomes 20, this becomes 100, this becomes negative 100, this becomes negative 20, this becomes a negative 10. So where is this trending? Well, it's trending upwards and it's continuing. It's getting bigger and bigger and bigger upwards. This is actually trending towards infinity, whereas this is trending towards negative infinity. Right? And so rather than write those limit statements as I wrote, just to save us a little bit of ink here, I just wrote what the values were, 5 and 5. But what I do want to write here is that the limit as x approaches 0 from the left is not equal to the limit as x approaches 0 from the right, and therefore the limit as x approaches 0 of f of x, d, and e. And we probably could have figured that out graphically, but I want to show the math because we know that this is the shape of that function and that as we approach 0 from both sides, we don't get one predictable value for what this function's behavior looks like at that point because of the vertical asymptote there. Great. So there's some examples. Now, another set of really important limits that we want to talk about are things called infinite limits. Right? An infinite limit is when you take the limit of some expression as it approaches infinity. Well, why would we do that? Well, oftentimes in physics, what we're caring about is what happens after a really long time. Well, in physics, what's a really long time? Well, if I look at it an infinite amount of time later, I can figure out the behavior of that function after a really long time, like when things settle, right? That's an important idea. Another thing to do is, especially in fields and gravitation and whatnot, is what happens when you're really, really, really far away from things. So the limit as some radial value approaches infinity to see what happens to that function, right? Because what happens, for example, gravity, if I've got a mass here and I have a little mass there that's feeling a force, well, we know that the magnitude of that gravitation force is big G m1, m2, if this is m2, over r squared. So what happens to that when this mass gets really, 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 really far away? Well, one way that we can do that is by examining the limit. What happens is the limit as r approaches an infinite value. Well, we can do that, and so what we get here is limit as r approaches infinity of f of g becomes, and functionally what you do is you plug in that infinite. Now infinity squared is just infinity, and that is equal to 0. So what happened there? Well, the numerator, or the denominator got so big there that what we would say here is that the denominator exploded. And anytime the denominator explodes on a term, gets really, really big compared to what's happening to the numerator, then that limit will go to 0, right? So there we go. Now another example, let's go back into the more prosaic here. F of x is equal to x squared plus 3. If I take the limit of this as x approaches infinity, right? That's going to be equal to essentially infinity squared plus 3, which is infinity. Okay? Now, there's no numerator there technically, but there is because everything is over 1. And if something here explodes to infinity, we would say the numerator explodes. Now, when I write these things, that's actually the work you're going to show, folks. If you were to just give me here, not this step, but just go right here to infinity and just cite that the numerator explodes, that's bueno, right? That's what I'm going to see. Now, things get a little bit messier when our expressions are a little bit more complicated. So if I talk about the limit as x approaches, say, infinity of the expression, let's say the expression is negative x to the fifth plus x squared plus 4, well, what do we have there? Well, technically, if I plug in, I've got negative infinity to the fifth plus infinity squared plus 4. Now, if you look at this, I'm going to have negative infinity plus infinity, really, like, is what that comes down to. But don't let that fool you, because if we were to do this on a table, you would find that this term is trending towards negative infinity a lot quicker than this term is trending towards positive infinity. And therefore, the answer here is negative infinity. So what we're going to have to do here is also look at the signs of our terms. Now, that also gets really interesting if I've got the limit as x approaches negative infinity of the same expression. Okay? And so that's going to be a negative infinity to the fifth plus negative infinity squared plus 4. Once again, I don't have to show this term. This would again be the numerator explodes, except that it's exploding to negative infinity. How do I show that? I'm just doing a little sign analysis here, right? And so here, negative infinity to the fifth, that's negative infinity times negative, that's a positive infinity. And that's, once again, the numerator explodes. So really what I needed to do here is I didn't need to do the lower terms. I could just ignore the smaller terms and only do a sign analysis of the leading term or the highest term here. So showing this and this is relevant. Now it gets a little bit more interesting now when I have a fraction. So limit as x approaches infinity of, say, x squared plus 4x plus 5 over x to the fifth plus 2x plus 3. Now, technically, this is a really complicated problem, but we're not going to make it complicated, because what we're going to notice here is that this, using the same logic from above, this is going to trend towards infinity, this is going to trend towards infinity, but because the highest order here is 5, this trends towards infinity faster than this was. This is just going to be 0, and we're going to say the denominator explodes and be done with it. Done, done, done. How are you technically supposed to do this? Oh, you're going to hate this. But really what you're supposed to do is the limit approaches x, and you're supposed to transform this function. So 1 over, this becomes 1 plus 4 over x plus 5 over x squared, and you factor out a x squared from the top, and then you factor out an x to the fifth in the bottom, 1 plus 2 over x to the fourth plus 3 over x to the fifth, x to the fifth, okay? And then what you do here is, remember that I can distribute this limit both separately to the top and to the bottom, and then separately to each of the products, and then inside here to each of these terms. So the limit of this expression would technically become 1 plus, and if I take the limit as x approaches infinity of this, I get a 0, and this, I get a 0, over 1 plus 0 as well, and then I just have x squared over x to the fifth, which becomes 1 over x cubed, and then very clearly you see the denominator explode. This is technically the work that you would have to show, and I would need to have, by the way, a limit as x approaches infinity here and a limit as x approaches infinity, and show all that distribution. Oh God, I don't want to do that nonsense. Boom, I'm done. Denominator explodes, done. Okay? Or if you want to do the proper, you can. Let's choose not to. Okay, a couple more things there. Limit as x approaches infinity of x to the sixth plus x to the third plus x plus 7, boom, x to the fifth plus x squared plus 4, right? Well, what happens here? Okay, well, we look at for our highest order term, boom, this is just going to be equal to infinity. The numerator will explode. Okay, now let's look just at a slight variation. This limit as x approaches negative infinity for that same expression. Here, folks, what we need to do is we have to do a little sign analysis, because we'll ignore the lower terms in each of these, right? We know they're going to infinity slower, but if we look at this, what I'm going to end up with here is I'm going to end up with infinity to the 6th, negative infinity to the 6th, over negative infinity to the 5th, and what I'm going to end up there with is a positive over a negative. And so that's going to mean that the whole expression will be negative. So here the answer is negative infinity. So what work would I need you to show with this? What I would need you to show here is this sign analysis as a separate piece, and then the infinity pops out and you would say numerator explodes. So I need the sign analysis, and I need whether the numerator or the denominator explodes. All right. Last example before we do some more examples there in a later video. So the limit as x approaches infinity, and I think you guessed what I'm going to do here, x to the 3rd plus x squared plus x plus 2 over x cubed, let's say 4x cubed plus 2x squared minus x minus 3. Well, what happens here? Well, we could go back and do this sort of analysis all the way through in the way that I did that about like pulling out the highest term and seeing what's left, or we can take the shortcut. And the shortcut here is looking at only the highest order terms. And what we say, it's actually almost silly, is what you do is if you just put your thumb over everything that isn't the highest order terms and look at just the coefficients of the highest order terms, there you have your answer. It's 1/4. And this is something that's called the thumb rule. So the thumb rule is used anytime you have a quotient of two functions that have the same highest order term, and all you're doing is you're putting your metaphorical thumb over everything that isn't those two coefficients, and then the ratio of the coefficients is the same thing as the ratio of those limits. So there you go. Those are your limit rules and how to do all those for all of your polynomial functions, and the basic ideas from here. It's just practice. So before we go, just one last thing. Remember, we try and plug in, see if we can do it. If that doesn't work, you get an indeterminate form. You see, transform the function. If that doesn't work, remember, at the end of the day, you can always numerically evaluate.